Today we're going to be starting notes on chapter 20, which is about electromagnetic induction. And the first section is about induced current. We're going to look at how we can change magnetic fields to create current. We're going to talk about something called Lenz's Law, which determines the direction of that current. And we're actually not going to do this last one. I do that with my pre-AP classes, but not the regular classes. Now, first of all, what does the word induce mean? You might have heard this word if somebody talked about maybe inducing labor or inducing a medical coma or something like that. What they are doing in those situations is causing that event to happen. So for a pregnant woman, they might to induce labor means to cause her to go into labor, or inducing a medical coma means to make them go into a coma for the purposes of healing. So the word induce means to cause something to happen. So when we talk about magnetic induction, when we talk about this, it's the process of inducing a current in a circuit using a magnetic field. So we are causing current to happen using a magnetic field. Now, in the previous unit, when we were building circuits, to create a current, we needed a source of potential difference or voltage called an EMF. When we were building circuits in class, we did that by using batteries. So batteries can provide a potential difference. But in this chapter, we're going to be talking about how to create current without a battery. You will get a current anytime a wire is moved through a magnetic field. Because what happens is, as the charges move through the field, the charges in the wire experience a force, a magnetic force, which causes the charges to move. And when the charges move, we get current. Now, there's actually three ways we can induce current. One way is to move a conductor inside a magnetic field. So, just as an example, let's say I had a horseshoe magnet. There is a magnetic field between the poles of the magnet that points away from the north and towards the south pole. And if I were to take a wire and move that wire in between the poles of the magnet, the wire, as it moved between the two poles, would kind of cut those magnetic field lines. Now, when I say cut, they're not severing the field lines, it's just passing through it. Now, another possibility is to rotate a conductor in a magnetic field so that your angle changes. So let's say I had a loop of wire inside here. If I had a loop of wire, or a coil, and then I rotated the coil inside the field, that would also create a current. Another way is to change the magnitude of the magnetic field. There's a couple of ways you can do this. For one, let's say you have an electromagnet. By changing the strength of the electromagnet, you can change the strength of the magnetic field created, which can create current in a different coil. Or you can move a permanent magnet towards or away from a coil. When you move the magnet towards the coil, you're increasing the magnetic field. When you move it away, you're decreasing it. And as you move it towards or away, you'll get a current going through the coil. Now, in all of these scenarios, there must be motion. If there's no motion, there's not going to be current. So there has to be motion when you compare the conductor and the magnetic field, one of the two has to be moving to create current. Because when they move, you cut your magnetic field lines. Again, when I say cut, I don't actually mean that they're cut. I mean that it passes through the magnetic field lines. So I mentioned before that you can actually take a coil of wire and a magnet and create current using just those two things. So let's say I had a permanent magnet. And a coil of wire. Now I'm using a dotted line here for a reason, because I'm going to be showing a magnetic field created, but I want to indicate that there's not actually a magnet inside the coil. So I'm using a dotted line to show that there's not actually anything there. Now if I were to take this magnet and push it towards the coil, what would happen is it would create a north pole on that side of the coil. And the field lines would actually repel one another. So let me put the south pole over here. We can use the right-hand rule to indicate the direction of the current. Now, right-hand rule, number 1, thumb points to the north pole, fingers curl in the direction of your current, so my current is going up here and like that. So by moving this magnet towards or away from your coil, we get a magnetic field created inside the coil, which creates current going through the coil. So we have if we have a spacecraft orbiting Earth and there's a coil of wire in it, an astronaut would be able to measure a very small amount of current in the coil, even though there's no battery connected to it and there are no magnets on the spacecraft. So if there's no battery, there's no magnets on the spacecraft, what is causing the current? Think about that for a second. The answer is that the wire is moving through Earth's magnetic field. And as the wire moves through Earth's magnetic field, it's cutting the field lines from that, which is creating current in the wire. Now, talking about a couple of things called Lenz's Law and Faraday's Law. Now, anytime we have an induced magnetic field, it is going to oppose the motion of the magnet. Like here, when I move the magnet towards my coil, the ghost magnet, is what we call this, repels the approaching magnet. So the ghost magnet is always going to act in a manner opposite of the magnetic field that is that's creating the ghost magnet. Which means, to paraphrase, that an induced magnetic field will repel an approaching magnet but attract a departing one. I'll show you an example of both of those in a second. The one we drew in example 2 was showing you the repelling one, but I'll show you the attracting one on the next slide. Now, Lenz's law tells us the direction of our induced magnetic field and therefore the current. There is something called Faraday's law that allows us to calculate several values in these scenarios, but we're not going to be doing that in this class. So, let me show you one more picture of Lenz's law. Now, unfortunately, the picture didn't come out as clear as I would like, but this is just another example of Lenz's law. Whenever we have a magnet approaching the coil, the ghost magnet created inside the coil repels the approaching magnet. And you can use right-hand rule for coils to determine the direction of the current that's created. But when the magnet goes away from the coil, a south pole is created on this side to try and attract it back. And again, right-hand rule number 1 can be used to determine the direction of the current. Alright, that's it for this section, and have a good day.